Today we are going to discuss about the ferroelectric properties of materials. So the previous chapter's dielectric properties are important for insulators and semiconductors. When a dielectric insulator is placed in an electric field, if the field is feeble or weak enough, it induces a polarization that varies linearly with the field, right? So the constant of proportionality determines the dielectric constant. Both static and time varying electric external fields are of interest, and the dielectric constant may depend on the frequency of the external field. So for typical dielectric at optical frequencies, there is a simple relation between the refractive index and the dielectric constant. So thus there is a close relation between the optical and the dielectric properties. In some solids, below a critical temperature, the polarization may freeze in. This is the phenomena of ferroelectricity. I will discuss in later on, which we will also discuss in the successive slides. Uh, we describe the ways the solids exhibit dielectric behavior as the and piezo, pyro, and ferroelectric behaviors. So proceeding on to the next slides. Oh, these are the basics of if my displacement current D is equals to D naught plus epsilon E, and in the same manner B can be written as B0 plus mu H, where epsilon and mu are the linear tensor operators, right? These two quantities, and the quantity epsilon is called the permittivity or electrical permittivity or dielectric function, and this is mu is the electrical permeability. The mu is called the magnetic permeability. If D naught is equals to 0, the material is called pyroelectric, and the change from D naught not equals to 0 to D naught equals to 0 takes place through a second order phase transition. I will coming later on. The materials is called ferroelectric. So for most materials, this D naught equals to 0. Even in the cases where D naught not equals to 0, the value is very small. So materials for which B naught is different from 0 are called ferromagnetics, likewise in case of ferroelectric materials. So proceeding further on, these all are called nonlinear dielectrics, where the materials have permanent dipole that interact to give a polarization in the absence of an applied electric field. So proceeding further on, a ferroelectric crystal is defined as a crystal which exhibits a spontaneous electric dipole moment, or a crystal for which even in the absence of an applied electric field, the center of positive charge does not coincide with the center of negative charge. So it can shown that that ferroelectricity possess in the crystal which lack a center of symmetry. So all ferroelectrics will be piezoelectric, but not all piezoelectrics will be ferroelectric. Such an example is quartz. Um, Actually, the occurrence of ferroelectricity is interpreted to be uh, the result of a polarization catastrophe. So there are total 32 different symmetry point groups, 21 of which do not possess a center of symmetry. This asterisk in this table possess centrosymmetric crystal, and their symmetry includes the center of inversion. But in case of piezo, pyro, and ferroelectricity, out of 32 different crystal point groups, these 21 of which do not possess a center of symmetry. Ferroelectrics are part of a small subgroup of these non-centrosymmetric crystals. Dielectrics belonging to all but one of the groups of non-centrosymmetric crystals are piezoelectric. So these are the 6 systems: triclinic, monoclinic, orthorhombic, tetragonal, hexagonal, and isomeric. So proceeding further on, this is the simple quartz. As you can see, uh, as I have mentioned, the material can be either piezo, pyro, or ferroelectric only if its crystalline symmetry is inherently asymmetric, that it lacks an inversion center. A crystal must have at least the symmetry of the point group of the crystal. Thus, the above properties, which are inherently asymmetric, can only arise in asymmetric crystals. The 32 crystal symmetry classes, as I have shown in the last slide, 11 exhibit center of symmetry. In another one case, a combination of symmetries effectively provides such a center, leaving 20 classes which have asymmetric properties. All the crystals in these 20 classes are piezoelectric. So, definition where this piezoelectricity comes in quartz. So, when such a non-centrosymmetric crystal is subjected to a mechanical stress, the ions are displaced from each other in an asymmetric manner, and the crystal becomes electrically polarized. This is called piezoelectric effect. As shown in the figure, if there is no stress, there would be no voltage difference. And if you elongate this or stretches this molecular structures or the ionic structures, these positive charges align in one direction and negative in another direction. Same case occurs in case of compression. So two type of atoms are here, so silicon dioxide. So what is basically piezoelectricity is that, okay, this one. So piezoelectricity arises when some external force has been applied as mechanical stress, and the force is strong enough to displace the ions in an asymmetric manner, and the crystal becomes electrically polarized. So as can be seen from this, if we stress this material, if this is a piezoelectric material, PZT is the lead zirconium titanate, is the well-known piezoelectric material, and the voltage difference shows the non-zero value. So the appearance of the electric potential across certain phases of a crystal when it is subject to a mechanical stress are called piezoelectricity. The piezoelectric effect is often used to convert electrical energy into mechanical energy and vice versa. The inverse effect of it, that is an applied field produces strain, has also been observed. Quartz is the most familiar piezoelectric substance and the one most frequently used in transducers. So, in an household use, this piezoelectric effect is very much evident in the gas lighter. When we press in the gas lighter, the mechanical stress are being converted into an electrical spark. So the existence of the direct effect and its inverse is to be distinguished from a similar kind of property called electrostriction. The inverse of piezoelectric effect and the electrostriction are more or less similar, but in this electrostriction, the material becomes strained in an electric field E, and this electrostriction is proportional to E square. Hence, there does not exist any inverse of this effect, like piezoelectricity. So this can be shown from these figures. As I have mentioned, this is this yellow portion at the center of the negative charge, and yellow plus is the center of the positive charge, and these two are not coincide in case of non-centrosymmetric crystals. And we apply mechanical stress, the crystal gets compressed or crystal gets elongated. These separation of charges are separated enough to develop a electric field, voltage difference, which we call the piezoelectricity or inverse of piezoelectricity. This is a very important diagram I have found in internet, where this kind of perturbations, sigma is the mechanical stress, is the electric field, temperature, and magnetic field, how these perturbations uh, responded by the physical parameters, which are our uh, concern, like piezoelectric, dielectric, pyroelectric. This type of behaviors are being observed. These are the perturbations, these are the responses. These are interconnected by this simple diagram. Moving further on, crystals in uh, 10 of the 20 classes have a unique polar axis. What is polar axis? Where none of the point group operations turn the axis round, responsible for the appearance of a spontaneous electric polarization, even in the absence of the electric field. A change in the temperature delta T, as I have mentioned, this one, the change in the temperature delta T of the crystal produces a change in the polarization delta P according to the relation delta P is equals to lambda delta T, where lambda is the pyroelectric coefficient, which can be measured experimentally. This effect is called the pyroelectric effect and can be produced either by heating or cooling the crystal, right? So the simplest pyroelectric crystal is woodsite. What is the hexagonal zinc sulfide structure projected on the 0, 1, 0 plane? This kind of behaviors, this kind of crystal structures, which turns out to be hexagonal, and the crystal class is 6 millimeter, for which the polar axis and PS, spontaneous polarization, are parallel to the C axis and 6-pole symmetry axis. When a woodsite crystal is heated, it undergoes an anisotropic thermal expansion, The resulting change in the C by A ratio accounts for the fact that woodsite is a pyroelectric as well as piezoelectric. On the other hand, the same kind of zinc sulfide, a non-centrosymmetric sphalerite, so when a non-centrosymmetric sphalerite, which is the cubic structure of zinc sulfide of the same material, is heated, the four equivalent directions in 111 expand uniformly. Therefore, sphalerite, being the same family of zinc sulfide, is piezoelectric but not pyroelectric at all. So this is the phenomena of pyroelectricity, which arises typically for the application of temperature, and the temperature gradient is directly proportional to the change in the polarization. So moving further on, if we're going to discuss the ferroelectricity or the spontaneous polarization which is being arised, so a ferroelectric material like a ferromagnetic one exhibits a spontaneous polarization even in the absence of an external electric field. The spontaneous polarization gets destroyed and the ferroelectricity disappears above a certain temperature called the transition temperature or the Curie temperature, we will discuss later on, where the materials becomes paraelectric, where there is no net polarization at all. This figure illustrates the temperature dependence of the polarization in ferroelectric crystals. A phase transition from the paraelectric to the ferroelectric or vice versa is accompanied by a change in crystal structure such that the ferroelectric phase is well ordered, like this one, has a lower crystal symmetry than the paraelectric one. So the occurrence of the ferroelectricity may be understood in terms of either the polarization catastrophe or the transverse optical phonon mode. So a typical behavior uh, of these ferroelectrics are below a certain temperature called critical temperature or Curie temperature, the spontaneous polarization is destroyed by the thermal disorder and the material exhibits the dielectric hysteresis loop. The description is based on the domain structure of ferroelectrics. When the dipoles in a crystal are randomly oriented, there is no net polarization. When the field is applied, the dipoles begin to line up with the electric field. The total dipole moment changes either by the movement of the walls between the domains or by the nucleation of new domains. Eventually, the field aligns all the dipoles and PS or the spontaneous polarization obtained. When all the dipoles are aligned in the same direction, the material is poled. When the field is subsequently removed, a remnant polarization pair exists due to the coupling between the adjacent dipoles. The material is permanently polarized in the absence of an electric field. This property is the key to ferroelectricity. When the direction of this E is reversed, the dipole orientation switches to become aligned with the new field direction. As the strength of the reverse field is increased, PS, that is the spontaneous polarization, will eventually occur with the opposite polarization. as the field alternates, a hysteresis loop is produced. The area contained within the loop is related to the energy required to cause the polarization to switch directions. So as the strength of the reverse field is increased, this PS is eventually occur with the opposite polarization. As the field alternates, a hysteresis loop is produced. The area contained within the loop is related to the energy required to cause the polarization to switch directions. Linear dielectrics, this linear dielectrics, which are most of them do not show significant hysteresis in an alternating electric field, but there is a structural requirement for ferroelectricity. There are a total 32 different symmetry point groups, 21 of which do not possess a center of symmetry. Ferroelectrics are part of a small subgroup of these non-centrosymmetric crystals, what I have discussed. So dielectrics belonging to all but one of the groups of non-centrosymmetric crystals are piezoelectric. So this is the typical hysteresis curve for a typical ferroelectric substance. We can infer that all ferroelectrics are pyroelectric and piezoelectric. All pyroelectrics are piezoelectric. All piezoelectrics are not pyroelectric. And lastly, the pyroelectrics are not ferroelectrics. This can also be inferred from this chart or diagram, this one. Out of 32 symmetry classes, these 21 non-centrosymmetric crystals are our point of interest, out of which 10 are pyroelectric, 11 are non-pyroelectric. These 20 are piezoelectric crystals. So pyroelectric comes under this piezoelectricity, and ferroelectricity is the special case of pyroelectricity. So this can also be inferred in this fashion. Going on to the domain structures, like in the previous slide, this one. Ferroelectrics are composed of permanently polarized regions called domains. These are the one, two, three, four. Four domains can be seen from this figure. In the absence of an electric field, these domains are randomly distributed, as you can see by these dipoles, direction of the dipoles, so that the net macroscopic polarization field is zero. When an electric field is applied, the dipoles tend to align with the field so that the domains with the polarization component along the field grow at the expense of the non-aligned domains. Ferroelectrics typically have very high permittivities such as barium titanate. The domains do not respond directly with the electric field, as domain orientation and growth is not a reversible process but involves losses. Okay, the polarization P is then non-linearly related to the electric field E by the hysteresis curve shown in this figure. The polarization of an initially unpolarized sample increases with electric field in a non-linear way until the saturation value PS is reached, when all the domains are completely aligned with the field. A further increase in E does not increase P, as all the dipoles are completely aligned in this curve. So as the field decreases from the reverse fashion, the polarization does not retrace. If it goes from zero like this, it takes another path apart from this path, does not retrace its path, but follows a new path as the dipoles tend to stick to their previous position. Even when the electric field is zero in this origin, remanent polarization PR remains. To bring the polarization to zero requires a negative coercive field minus EC. Further magnitude increases in negative electric field continues the symmetric hysteresis loop until negative saturation is reached here minus PS, where all the dipoles have flipped over. If all are dipoles pointing up in this fashion, in the lower point all are pointed down in this minus PS position, means all the dipoles have flipped over. So in this condition, if the field is now brought to zero, field is brought to zero, and continued to positive field values, the whole hysteresis curve is traversed. So from zero, if we go on increasing E, goes like that. Then if we flip the direction of the electric field, it traces a new path apart from this path and go to the remanent polarization, and the highest value is the saturation polarization. In the remanent polarization, our electric field is zero. It comes to minus EC where our polarization becomes zero. It goes back. Then in this position of minus PS again, our electric field becomes zero, and this whole process is a closed loop which is called the hysteresis loop and been exhibited by the typical ferroelectric crystals. So all ferroelectric crystals are polar crystals. Uh, the term ferro is used, but iron has nothing to do with it. Low symmetry causes spontaneous polarization. Because of their structure, polar crystals have a permanent dipole moment. If rho v is the total charge density, we know the polar crystals integration r rho r dv not equals to 0. The pyroelectric crystals have a polarization that changes with temperature. All polar crystals are pyroelectric, but not all polar crystals are ferroelectric. Ferroelectric crystals are polar crystals whose polarization can be reversed by an applied field. All ferroelectric crystals are also piezoelectric, in which stress changes the polarization. Piezoelectric crystals are suited for making electromechanical transducers with a variety of applications. So ferroelectric crystals often have unusual properties. Rochelle salt, that is NADP, NaKCH C4H4O6 4H2O, which was the first ferroelectric crystal discovered, has both an upper and lower transition temperature. The crystal is only polarized between the two transition temperatures. The TGS type of ferroelectric, including triglycerine sulfate and triglycerine selenate, is another common class of ferroelectrics and has found application to IR detectors due to its pyroelectric properties. Ferroelectric crystals with hydrogen bonds, that is KDP, K is to PO4, which was the second ferroelectric crystal discovered, undergo an appreciable change in transition temperature when the crystal is deuterate. BaTiO3, shortly named as BT, was the first mechanically hard ferroelectric crystal that was discovered. Ferroelectric crystals are often classified as displacive, involving lattice distortion, that is barium titanate BaTiO3, or order disorder transition. So going to the more different process, these two curves where the temperature versus polarization shows The first order, this is the discontinuity in this region, and the second order, completely continuous curve below TC, spontaneous polarization exists. This figure gives the first and second order transitions of paraferro transitions. This is a more particular curve, comes from the thermodynamics of ferroelectricity, or rather the Landau theory. This is the Landau equation for both first order where gamma less than 0, where the latent heat G continuous, and second order where gamma greater than 0, no latent heat, that is the first derivative of G, are continuous. We can choose delta equals to 0 and assume that the Gibbs free energy G prime. So G is equals to G naught plus half beta T minus T naught P square plus 1/4 gamma P to the power 4 plus 1/6 delta P to the power 6, where beta delta greater than 0. By symmetry, only even powers are possible. Also, in a second order transition, P is continuous. This one, P is continuous at the transition temperature Tc, whereas in a first order one, it is not. So from this we can calculate E, which is the first derivative with P, that is del G del P, turns out to be beta T minus T dot P plus gamma P cube plus delta P to the power 5, and the inverse of the susceptibility chi is equals to del E del P, beta times T minus T naught plus 3 gamma P square plus 5 delta P to the power 4. Notice importantly in this state, in the paraelectric phase where our P is equals to 0, so E is also 0, and chi becomes 1 upon beta times T minus T naught. And therefore, Curie-wise law behavior is here. So for T less than Tc and E equals to 0, for second order where delta equals to 0 and beta times T minus T naught P plus gamma P cube is equals to 0, where P square is equals to minus beta upon gamma T minus T naught, or P is equals to plus minus root under beta by gamma T naught minus T, which is again a Curie-wise behavior. We assume that gamma greater than 0. For T equals to Tc equals to T naught, we can show that the stable solution is the polarized one. So from this equation of Landau, one can find that the transition temperature is T naught plus 3 gamma square over 16 beta delta. So actually the ferroelectric transition comes from the, as I have mentioned, from the polarization catastrophe. Suppose we have n permanent non-interacting dipoles P per unit volume at temperature T in an electric field E at higher temperatures. Simple statistical mechanics shows that the polarizability per molecule is alpha is equals to P square upon 3 kT, comes from the orientational polarizability as we have shown in the last chapter. So combining this with the Clausius-Moussorti equation, this gives epsilon by epsilon naught is equals to 1 plus np square by 3k epsilon naught T minus Tc. As T tending to Tc, we obtain the polarization catastrophe. For a real crystal, even if this were a reasonable approach, the equation would break down well before T equals to Tc, and at T equals to Tc, we would assume that permanent polarization had set in. Near T equals to Tc, we have essentially a Curie-wise type behavior. Another way of reviewing the ferroelectric transition is by the Leiden-Such-Steller equation, LST, that is developed in the next uh, discussion, where the infinite dielectric constant implies a zero frequency optical mode. And this leads to the Cochen's theory of ferroelectricity arising from soft optic mode. The LST relation can be written as omega t square. This is the transverse one, this is the longitudinal one, and the ratio of the square are the epsilon infinity over epsilon 0, where omega t is the transverse optical frequency, omega l is the longitudinal optical frequency, both at low wave vector. Epsilon infinity is the high frequency limit of the dielectric constant, epsilon 0 is the low frequency, that is the static limit. Thus, the Curie-wise behavior for epsilon 0 is 1 upon epsilon 0 is proportional to t minus tc, is consistent with omega t square is proportional to t minus t. So these are the typical selected ferroelectric crystals table, where this type of KDP, K is to PO4, causes the transition temperature or Curie temperature of 123 Kelvin, the triglycerin sulfate 322 Kelvin, perovskite structures like barium, lead, or lithium niobium oxide causes 406, 765, and 1483 Kelvin. So one effect of the local field is to reduce the frequency of the transverse normal mode of the lattice, like this: omega t square equals to omega naught square minus 1 upon mu 1 upon 3 epsilon naught n by v e star square over 1 minus 1/3 n by v alpha for sufficiently large effective charge E star, high electronic polarizability alpha, or relatively weak coupling to nearest neighbors, and the transverse frequency can even become zero. The local field associated with the movement of an ion is the lattice is then so strong that the repulsive forces due to nearest neighbor interactions are smaller than the forces due to this field. So the resultant force displaces the ion from its usual position until it reaches a new equilibrium position. The forces occurring in this situation are not included in this harmonic approximation. The new state of the solid is characterized by the decomposition into regions with permanent polarization. This effect is called the polarization catastrophe, and in analogy to ferroelectromagnetism, the new state is called the ferroelectric state. And typical ferroelectric materials are perovskites like BaTiO3 or strontium titanate, and hydrogen phosphates or arsenates, that is K2PO4. The ferroelectric state can be regarded as the frozen in transverse photon, and the prerequisite for this freezing in is that the thermal motion of the lattice is small. With increasing temperature, the thermal fluctuations become ever larger, and the effective field at the ion is thereby reduced until at a critical temperature Tc, uh, the right side, this one, becomes positive. As the temperature increases beyond Tc, the transverse frequency increases according to this one, omega t square is proportional to T minus Tc. From the Leiden-Such-Taylor relation, the static dielectric constant is approximately epsilon inverse is proportional to T minus Tc. The dielectric constant remains finite on approaching Tc. A schematic presentation of this relationship is shown in this figure. On account of their large dielectric constants above the Curie point, ferroelectric materials, in particular ferroelectric ceramics, are of great technological importance as dielectrics in capacitors. Below the Curie point, the ferroelectric ceramics have a large piezoelectric constant. Ceramics with suitable Curie points are utilized as piezoelectric actuators. Ferroelectric nanostructures serve as non-volatile memories in advanced computers. This is the curve of temperature dependence of the permanent polarization P and the reciprocal dielectric constant, static dielectric constant, and the square of the transverse frequency omega t square for a ferroelectric material.